This is part 2 of what is a function. I wanted to separate this into 2 videos because it was a lot of material. Let's look at another example of using a function. If an astronaut weighs 130 pounds on Earth, then her weight when she is h miles above the Earth is given by the function w of h is equal to 130 times 3960 over 3960 plus h squared. What is her weight when she is 100 miles above the Earth? Well, all you have to do is find out what w of 100 is. So I'm going to plug in 100 for h. Make that look more like a 3960 minus 100 squared. I'm going to plug that into my calculator, and I'm going to find out it's approximately 123.67 pounds. Next, let's construct a table of values for the function w that gives her weight at heights from 0 to 500 miles. What do you conclude from the table? Well, if I'm going to make a table, then the first column is going to be the height, and the second column is going to be the output, which is the weight as a function of height. And probably the best way to make this table is to make the height in 100. So instead of like 0, 1, 2, 3, 4, 5 all the way to 500, we're going to do 0, 100, 200, 300, 400, and 500. And this will give us a pretty good idea of what happens. So when her height is 0 miles above the Earth, she weighs 130 pounds. We found out when she was 100 miles above the Earth, she weighed 124 pounds. When she's 200 miles above the Earth, if you plug in 200 for h, you'll find out she's 118 pounds. At 300 miles above the Earth, she is 112 pounds. At 400 miles above the Earth, she's 107 pounds. And at 500 miles above the Earth, she's 102 pounds. Well, what's happening is the more miles above the Earth's surface that she is, the less she weighs. Now let's talk about finding domain. There are some things you need to remember when finding domain, or what values can be plugged into a function. First of all, when you deal with a fraction, you can never have 0 in the denominator of a fraction. When dealing with a radical, you can never have a negative under a radical. You can have 0, though. So when you're finding the domain of something like part A, any number can be plugged in as long as it doesn't make the denominator of this fraction 0. So we're going to say that the denominator, x squared minus x, cannot equal 0. And in order to find out what values of x can make it 0, we're going to factor and solve using the zero product property. So I can factor out an x, and then I find out that x cannot be 0, and x cannot be 1. Another way of writing the domain is to say that x can be all the numbers from from negative infinity all the way to 0, non-inclusive, and all the numbers between 0 and 1 can be plugged in, non-inclusive, and all the numbers from 1 to positive infinity can be plugged in. For part B, the part that's under the square root sign cannot be negative. It's got to be greater than or equal to 0. Now 9 minus x squared is kind of interesting because you can factor it into 3 plus x and 3 minus x. Now in order to find out the domain, what we do is we make this little chart, like a little number line. And the values of x that make this inequality 0 are when x is 3 and when x is negative 3. So what it does is it kind of breaks the number line into 3 divisions. The stuff that's less than negative 3, the stuff that's between negative 3 and 3, and the stuff that's greater than negative 3. And what we want to find out is in each of those 3 intervals, are the values greater than 0 or less than 0. We're going to use a plus sign if they're greater than 0 and a negative sign if they're less than 0. Because we want to know in what region this graph is greater than 0. So if I start and try like -4, which is off to the left of -3, if I plug in -4 for x, I get 3 plus -4, which is -1, times 3 minus -4, which is 7, and 7 times -1 is a negative. Is -7 greater than 0? No. How about the numbers that are between -3 and +3? So how about I try 0? 3 plus 0 is 3, 3 minus 0 is 3, 3 times 3 is 9. Is 9 greater than 0? Yes. And how about if I try a number that's off to the right of 3, like 4? 3 plus 4 is 7, 3 minus 4 is -1. You're going to get a negative, which is not greater than 0. So where does this domain exist? This domain exists between 3 and -3. Or you can write it like this. Now the last function, not only do we have to deal with the fact that there's a radical, but we also have to deal with the fact that that radical's in the denominator, and you can't have 0 in the denominator of a fraction. So there are a couple things going on here. One of the things is that, well, or we can do this. Instead of saying that what's underneath the radical has to be greater than or equal to 0, we're going to just say that what's beneath the radical has to be greater than 0. Because not only does it have to be positive, but it can't equal 0. So t has to be greater than -1. In interval notation, we would write that as -1 comma infinity. There are 4 ways to represent a function. The first way is verbally. That means saying what a function is. For example, this here is a verbal description of a function. The second way is algebraically. If you take words and you write them as an algebraic equation, that's an algebraic way of showing a function. So let's start with that. To convert from Celsius to Fahrenheit. So to find the function f of c, first you multiply the Celsius temperature by 9/5, and then you add 32. And that is the algebraic way of representing that function. Numerically means making a table. So if I'm going to make a table, the input is the Celsius temperatures and the output are the Fahrenheit temperatures. And there's really no rule for how I make this table, so I could start at like -10 degrees and then do 0, +10, +20, +30, +40, just to get an idea of the Celsius temperature's relationship to Fahrenheit. So now if I use that equation, I want to know what is the Fahrenheit equivalent of -10 degrees Celsius. -10 times 9/5 plus 32 is going to tell me that it's 14 degrees. When Celsius is 0, Fahrenheit's 32. When Celsius is 10, it's 50. When Celsius is 20, it's 68. When Celsius is 30, it's 86. And when Celsius is 40, it's 104. And the last way to represent it is graphically. Well, or I shouldn't say graphically, but visually. And visually means make a graph. So if I were to make a graph, my x-axis I can make every 10. And my y-axis I need to at least go from 0 to a little over 100. So probably the best way to do this is to go by tens. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So when it's -10 degrees, it's about 14. When it's 0, it's 32. So 10, 20, 32. When it's 10, we said it was about 50. When it was 20, it was about 68. when it was about there, when it was 30, it's about 86. And when it was at 40 degrees Celsius, it was about 104. And what you'll find out is that the conversion is awfully linear.